The DigiArcheoSpace project aims to modernize the higher education by providing educational materials and modern tools for documenting and presenting the cultural heritage in archaeology, digital archaeology. The developed competence framework, learning management system, movies, guide, and training activities will improve the knowledge and skills of the target group, professors/teachers in universities, archivists, and experts working in the area of digitization of archaeological cultural heritage. The project is a combination of development, training, exchange of experience, and dissemination activities including development of competence framework and learning management system using microcredentials approach, development of educational videos, guides, and other materials suitable for higher education, training activities and exchange of experience in the area of digital archaeology, dissemination of the results among higher education organizations and other educational/training organizations. Archaeological field research is unimaginable without technical documentation. It implies the creation of topographic bases, i.e. plans and maps. The most commonly used method for topographic surveying of the terrain is the tachyometric method. This method uses a theodolite tachyometer instrument, or more recently, a total station. The total station is an integrated modern instrument for surveying that combines an electronic theodolite, electronic distance measurement, EDM, and computer software for precise measurement of angles and distances. It is used for surveying of the terrain. That is, in our case, for calculating positions of points and heights. Total stations not only have the ability to digitally measure and display angles and lengths, but also process the measured quantities, giving desired solutions as a function of the measured values. These values can be displayed on the display of the instrument, or stored in the internal memory of the instrument, or recorded on another medium for further processing. To begin applying the tachyometric method of field surveying, we first need to have at least 3 points with known coordinates and altitudes. Point S. That is the station point where the total station is set up. Point O. The orientation point that serves as our orientation. Point C. The second orientation point that serves as our orientation control. To start measuring, the instrument needs to be fixed on a tripod, then placed on the known station point that is defined by its coordinates. In our case, the values of that point and other orientation points were previously determined with a GPS RTK instrument, because the state georeferenced points were very difficult for us to access. We will talk about GPS RTK later. Once the instrument is fixed to the tripod, the placement of the instrument on a point is done using a plummet plumb. In our case, the plummet plumb is optical. There are also laser plummets on other total stations. Next step is centering and leveling. Centering and leveling is done using the circular level and plate level of the instrument. That is, the vertical circle of the instrument should be under 90 degrees with the horizontal circle. We level the circular level and plate level of the instrument with the tripod legs and the tribrac screws. Next, we determine the height of the instrument with the help of a meter. We measure the height distance from the instrument telescope to the station point. We memorize the resulting height difference in the instrument. Next, the prism is placed on the prism pole. Then, the height of the prism is determined, and the specified height is entered into the instrument. Depending on the field of view of the total station's telescope, the height of the prism may be adjusted during the measurement if necessary. The total station is aimed at the prism. The measurement is performed by using the total station to measure to another first known point that serves as orientation, then we measure again to a second, also known point that serves as control. Based on the occupied horizontal angle between the orientation and the recorded control point and based on the horizontal distance between the station point and the control point, the position of the recorded control point is defined, the values of which should match the values we have from before. If the values match, we can continue using the same principle to determine the new points. Most often, we export the recorded new points to CAD software intended for technical drawing. In addition to total stations for determining the positions of points, the application of Global Positioning System or GPS technology also plays a major role today. The complete GPS configuration consists of 3 segments. Space segment, satellites that orbit the Earth and transmit signals. The space segment is designed to have 24 satellites orbiting the Earth at approximately 20,200 kilometers every 12 hours. Currently, more satellites are orbiting the Earth. The space segment is designed to have at least 4 visible satellites that subtend an angle of more than 15 degrees at any time at any point on the Earth. Experience shows that usually at least 5 satellites are visible in this way, and most often it is about 6 or 7 satellites. The satellites constantly transmit radio waves and light waves. Control segment, stations positioned on the ground near the equator to control and monitor the satellites. The control segment consists of 1 main control station, 5 monitoring stations, and 4 ground antennas placed at 5 locations along the equator. The control segment controls the movement of the satellites and calibrates and synchronizes their clocks. An important function is to determine the orbit of each satellite and predict its path for the next 24 hours, so that it knows where each satellite should be expected to be. The user segment represents each GPS receiver that receives the GPS signal for the purpose of determining the position. Each GPS positioning is based on measuring the distance from the satellites to the receiver on the ground. The basic idea is to obtain the spatial coordinates of the location of the receiver by intersecting the 3 measured distances from the satellites to the receiver. At least 4 satellites are needed to determine the location of the point. There are 3 different methods of determining the position of the GPS receiver. Autonomous navigation, where only 1 receiver is used. This is most often the case when a handheld GPS receiver is used and when determining the coordinates, an accuracy of 3 m is achieved. In archaeology, we use it to roughly determine some positions, most often during reconnaissance. Today, modern smartphones have this option built in. Next is corrected positioning, where a signal is received from a relatively close point on the ground with certain coordinates, base station, achieving an accuracy of 0.3 m. Next is corrected dual-frequency positioning. The difference from the previous method is that a dual-frequency receiver must be available, the use of which cancels the instability of the ionospheric influence and achieves an accuracy of 1 centimeter. When it comes to measurement techniques, RTK, real-time kinematic, is the most suitable technique for us, because we receive and store the coordinates in real time without the need for additional calculations. The biggest advantage of GPS over the total station is the fact that we do not need to detect, and also thicken the network of reference points. Very often these things are more complicated and more extensive than the recording of the detail itself. Then as an advantage we would state that visibility between any 2 points is not required, so the accuracy of the results and the need for fewer people to perform the tasks. However, GPS technology also has its limitations. The satellite signal can be blocked by objects or trees and it is impossible to record indoors. Therefore, it is often best to combine GPS and total station. Some manufacturers produce integrated instruments, GPS and total station in one. Digital cameras. One of the main parts of an archaeological field research is photo documentation. Today, thanks to digital cameras and drones, photo documentation is simplified and easier to post-process. With digital cameras, we document the situations of archaeological sites. We also document and post-process mobile archaeological finds. Photogrammetry is the science of obtaining reliable information about physical objects and the environment through the process of recording, measuring and interpreting photographs. It is most often used to create bases for the preparation of plans and maps, as well as for the preparation of 3D models. Photogrammetric surveys can be aerophotogrammetric using an airplane, drone, etc., or terrestrially performed from the ground. In our case, we will perform aerial photogrammetric surveying using a drone, a total station, and computer software for data processing. First, we place the markers on the ground, then we record their coordinates with a total station. In digital photogrammetry, markers are reference points used to accurately align and scale images. They help in identifying the same physical points across multiple photos to ensure precise 3D reconstruction and measurements. Next, we set up and calibrate the drone. We take off and start shooting stereoscopically. This means that we need to ensure at least 60 to 80% overlap between successive images, overlapping both from the side and from the front. For the sides of the object, we also shoot stereoscopically, only we straighten the camera gimbal by 90 degrees. After the field recording is completed, we begin software processing of the data. After the software processing is completed, we obtain a three-dimensional model of the actual state of the archaeological site. From here we can create measurement photographs that serve as a basis for mapping bases and sections. We perform the mapping in CAD software. Photogrammetry is a fast, precise, and very useful technique that is taking on an increasing role in modern archaeological practice. In addition to documenting archaeological sites, photogrammetry is also used to document movable archaeological artifacts. The artifacts are photographed from multiple angles and later processed using software. This gives us a virtual three-dimensional database of moving artifacts. A virtual three-dimensional database is very useful, secure, and far more accessible. In addition to photogrammetry, we also use a laser scanner to create a three-dimensional database of moving artifacts. A laser scanner for moving objects uses laser beams to continuously scan the environment. It emits pulses of laser light, which reflect off objects in the path of the beam. The scanner measures the time it takes for the light to return, creating a 3D point cloud or map of the surroundings. For moving objects, the scanner rapidly updates the data, tracking their position and movement over time. Virtual reconstructions. One key aspect is virtual reconstructions, where archaeologists create digital models of historical structures or artifacts based on available data, such as excavation findings, historical records, and imaging techniques. These virtual reconstructions help visualize ancient environments, allowing researchers and the public to explore and understand past civilizations in an immersive and interactive way, while also aiding in preservation efforts. One of the most exciting applications of digital archaeology is the creation of 360-degree virtual tours. These immersive tours allow users to virtually visit archaeological sites and explore them from the comfort of their homes. This technology offers an interactive experience that goes beyond traditional 2D photographs or text-based descriptions, enabling people to walk through ancient ruins, museums, and excavation sites in a way that was once unimaginable. 360 virtual tours are typically created by capturing panoramic imagery of the site using specialized cameras that capture high-resolution photos from every angle. These images are then stitched together to form a seamless, navigable virtual environment. Users can click on different areas of the site to zoom in on particular features, click on information markers for historical context, or even view artifacts in 3D. Such tours often include audio narrations, which provide additional layers of context, such as the history of the site, cultural significance, and findings from ongoing excavations. 360 virtual tours also democratize access to cultural heritage. For centuries, access to archaeological sites has been limited by geographic, financial, or political factors. With the advent of virtual tours, people from all walks of life can explore and learn about distant cultures and civilizations. Educational institutions, in particular, benefit from this technology, as students can virtually visit historical sites as part of their curriculum, expanding their understanding of ancient societies in a more immersive and engaging way. Digital archaeology and 360 virtual tours are revolutionizing how we explore, preserve, and engage with the past. By leveraging cutting-edge technologies, archaeologists are able to create detailed, interactive digital replicas of historical sites and artifacts, offering unprecedented opportunities for research, education, and public access. Through these non-invasive digital methods, archaeology becomes more precise, inclusive, and accessible. For students, it's not just about learning the past, it's about reshaping how we interact with it.